Welcome everybody to the 28th edition of the Multi-Omics reading group. I'm your host for today, Cesar Miguel de Córdoba, and today we have the absolute pleasure to welcome Erpai Luo from Tsinghua University, who Xinyu will now introduce and then give a talk in a reading group. Please, Xinyu, you may.
Hi everyone. Cesar, thanks for the nice introduction for the record and everything. So hi everyone. This is our Multi-Omics reading group, and it's our 28th edition. So let's welcome Erpai. He's from Tsinghua University. He's a second-year PhD student who's supervised by Professor Xuegong Zhang, who is also very famous in this single-cell omics study area. And also his research for Erpai focuses on single-cell generation model and foundation model, AI agent, and also another AI for science domain. Yeah, let's welcome him, and yeah, it's all yours. Thanks, Erpai, for accepting our invitation.
Okay. Thanks, Xinyu, for the introduction, and also thank you guys for inviting me to your reading groups. So, is everything fine with my screen and my microphone?
Yes, everything looks fine on your end.
Okay. Then, yeah, we're good. Then let's get started. So, today I'm very glad to be invited here to talk about our recent work, scDiffusion-X, and this model, this paper is supervised by Professor Xuegong Zhang and also Professor Qiao Liu, and also incorporate with Mingsheng and Weilei. So let's just get started. So at the very first beginning, I wanted to give a very short summary about this work, and that is use the denoising diffusion probability model to generate single cell data. And this brings out the question about why we use diffusion and what do we think a generative model can do in a single cell field, because this question that I've been asked for many times. So I wanted to make it clear as a background at the very first beginning. So as we know that the diffusion model is now very popular and also powerful model in the field of computer vision, that today we have a lot of fancy tools or apps that are based on the diffusion technology that can generate images, generate video, any kind of things that you want. So this brings us the problem, the question that can we use the ability of diffusion model in the single cell domain? So as we know that there is a very popular task in the field of image generation that is called image to image. And you can also call it image transfer or image editing, which inputs a given image and try to transfer into another image. For example, here you can give an image of a man and transfer into a woman. So this reminds us a lot of biological process like the development of cells or the development of disease, and also things like cell state transition, like gene perturbation, or also the recently very popular drug or molecular perturbations. So we want to know, can the diffusion model do the similar things in image? And we can use this model to do things like cell transition or to simulate this kinds of biologic process in the field of single cell. So with these very original ideas, we developed the very first version of scDiffusion, where we use latent diffusion models with classifier guidance method to control the generation process. We use this model to generate a lot of new single-cell RNA-seq data from the Gaussian noise. And also, I wouldn't go very detailed into this model. The most important task in this model is we simulate the development process of the cells. Like we given the model for example, the cell from day 1 and cell from day 3, and we try to use the scDiffusion to generate the cell in between. So this is what we do in the scDiffusion model. And based on this model, we think, can we extend this model to a multi-omics version? Like, can we join more modalities into this model? So we develop this scDiffusion-X, as you can see in this feature, in these figures. So this is an overview about our methods. As you can see that in the figure A, the scDiffusion-S is still remain latent diffusion model styles, where we need to first train an autoencoders, but this times we need to train different autoencoder for different modality of data. And after we train these autoencoders, we can encode the input modalities into corresponding latent representations. And notice that we use all pair data in the training of scDiffusion-X. So after we obtain this paired latent representation, we can use them to train multi-modal diffusion denoising models, which was shown in figure B and C. Like you can see a very classical diffusion process involve forward process and also reverse process, and very different, a slightly difference from the original scDiffusion is that we now encode the outer condition, external conditions with condition embedding, and we add that during the forward process, which means that the model is now generated in the classified free styles. And also in figure D, to leverage the information inherent in the multi-omics data, we developed this zero cross attention model, which is like a core module of the whole scDiffusion-X. So these modules use a cross attention mechanism to integrate the information from different modalities and do the generation. So after we obtain this model, we train that on paired multi-omics data, and we first evaluate the generation results. We design a lot of evaluation metrics from different aspects, and we also compare a lot of baseline models. And also we involve data of different scales. For example, different cell numbers, different gene numbers, and also different chromatin regions numbers. So the results show that the scDiffusion-S can generate realistic multi-omics data at different scale. So which is very good. Yeah. So after we generated the data, we want to see if this generated data can be used for data augmentations. So we generated the cell of the real cell type in the training data and use this generated data to augment the original data set. And we then use this augmented data set to do the cell type classification task. So as you can see in this table and figures, that the classifier can now better distinguish the cell from these small data sets after the data augmentations, which indicate that the statistical significance of these cells are enhanced, which we think could be very helpful for other downstream applications. Should I stop a little bit at here? Do you have any questions, or should we save the question at the last?
We usually have a dedicated question section at the end, but if anybody has any, now's a great time to ask them.
Okay, I see. So is there any questions?
Not for me at least, but anybody else, just put it in the chat, raise your hand, maybe intervene. Dylan, anything on your end?
I guess I'm not super knowledgeable about diffusion models, or I forgot some of the details, but I know there's different variants. Like there's a stable diffusion model that apparently is like easier to train, and then you have other variants that are maybe more complex to train. So I'm just curious about the variant that you used here, although you have the schematics here, but maybe if you could say a word on that.
So you wanted to ask what's the difference of this diffusion model and the stable diffusion model, or you just?
Is there a specific variant that you're using here that is, yeah, that someone who doesn't know about diffusion model could use as a way to guide our understanding of what architecture selection you did?
Okay, I see. So I will explain a little bit about the diffusion model. So the diffusion model is to learn the data distribution of the training data, and there are different kinds of diffusion as structure, as you mentioned. Basically, two kinds of diffusion. One is called classifier guidance, and the other is called classifier free. So the classifier guidance model is like the let me show you this. The classifier guidance is what we do at the scDiffusion version 1, that you need to use an actual classifier to see if the generated data satisfy your requirement, and the model will adjust the reverse process based on the classifier's guidance. And the other type of diffusion is the so-called classifier free, which include the stable diffusion you just mentioned, that it doesn't need an external classifier to guide the training process. The condition was encoded during the forward process of the model. So basically, like we do here, you can encode the condition through a condition embedding, or you can do like in the stable diffusion, which use the text to guide the model. And if you need to use the textual information to guide the model, you will involve more complicated modules like the language model parts. Yeah, so this is the difference between two kinds of diffusions, and we basically use the classifier free diffusion here. Yeah.
Okay, but in the previous work you used the classifier guided version.
Yeah.
Okay, thank you. Perfect.
Okay, so then let's move on. So next, we wanted to see if the scDiffusion-X model can do the modality translation task, which is, I think, a very popular task in the field of multi-omics. So let me again go back to my model figure to explain how we do this. So in the normal generation process, both the generated modalities comes from pure Gaussian noise. But in the task of modality translation, we will replace the inputs of one modality. For example, we will replace the RNA feature here with real RNA features. And for the other features, which is ATAC feature here, will remain Gaussian noise. And during the reverse process or during the generation process, the ATAC feature needs to borrow information from these real RNA features and generated the corresponding RNA features. So now you can input a real RNA feature and obtain its corresponding ATAC features. So this is the basic idea of doing modality translation with scDiffusion-X. So we translate a bunch of data, and we designed many matrices from different aspects to evaluate the results, and we compare to the result to the baseline models, and we found that the scDiffusion-X can capture accurate biological signals. Based on that, we further do a task called perturbations. And this is, remember that we need to give an existing modality to the model and translate it to another modality, right? So if we perturb the input modality, for example, we perturb several genes in the input RNA-seq data, and we can then translate that to the corresponding perturbed ATAC-seq data. So we do this, and we compare the result with the real experimental data, and we found that the change direction of these translated perturbed ATAC-seq data, the change direction of the key peaks in these ATAC-seq data are very similar to that of the experimental data. So this is about the modality translation and perturbation. And for these two tasks, we still got some work need to do, like involve more baseline and do more analysis about the perturbation. But these are still ongoing works. So then here comes the gene regulation mechanism. So in here, so remember that we use a dual cross-attention model in the denoising diffusion backbones, and we want to know what's going on during the model inference process, and can we give some, like some interpretation about the dual cross-attention models. But the first question is that the cross-attention was carried on in the latent space, and we need to first link the original genes and original peak with the latent element. So we designed this gradient-based approach where we calculate a gradient backpropagation for a specific latent element, and we can obtain the gradient magnitude for each input genes. And for these genes with high gradients, we think that they associate with the specific elements strongly. So with that methods, we first verify if we can use this to find out any cell type specific highly attended genes or peaks. So for example, here we can use the ATAC to RNA attention map. Notice that we have two attention map here since we are cross attention, right? So the ATAC need to see the RNA, and the RNA need to watch out the ATAC. So there's a two attention map. So for example, here we can take an average of ATAC to RNA attention map, and we can obtain the attention score of each RNA element in this specific cell type. And if we further use this gradient-based approach to analyze these elements with high attention scores, we can obtain a bunch of key genes that corresponding to these key elements and also corresponding to these cell types. So to investigate that, we do a geo-analysis for these key genes we found, and the results show that the geo we obtained are very related to the specific cell type, the corresponding cell types. And also we can find that the gradient magnitudes of marker genes for that cell types in these top gradient, how to say that, the gradient magnitudes of the marker gene of the cell types of that cell types rank significantly higher than other genes. So we can also do the same thing in the ATAC size. So to find if these key peaks we found are more informative. So we found out that the key peaks we found that are more likely to overlap with the regulatory elements. Yeah, so far, has anyone has any question? Because I guess there is a bit confused about this part.
Yes. Hi. Could you like explain like whether there will be any like computational challenges when you do the importance assignment to the peak regions, because the peaks, they are quite sparse. It's very hard to imagine like the gradients like gradient signals can actually reflect something meaningful in the peaks.
Yeah, so we actually do some filtering works here. Like we will select the peaks that have higher openness scores, and these peaks we think are more likely to corresponding to these element.
How many do you select?
Do you mean the thresholds or?
Yeah.
I'm sorry that I didn't remember that threshold specifically, but we do set a value about the chromatin openness, and also we want to further set a threshold for the gradient, but we haven't tried that yet.
Okay, thanks. It's just like because when you are training your model, you use the whole statistic, but now you are only using part of it. It's quite surprising that, like, it's still like the model still holds because you changed the.
Okay. Okay. I know your question. Because here we still input the whole ataxic data into the model. We just select the selection here happens during the backward process, or how do you say that? The model first inference with whole ataxic data, and when we analyze this regulatory mechanism, we do the backpropagation, starting from that element, and usually the higher the gradient of the input peak is, the stronger or the more likely it is to affect the latent elements in its downstream. So this is just a way to select the correlation peaks. It's not that we input this subset of peaks. We still input all the peaks together. We just select them by these methods.
Oh, thanks. Just to ask another question to clarify. Do you use the cell type as the signal for your gradient, or do you use the expression itself, like from those highly expressed peaks or genes, as the gradient signal to do the backpropagation?
No, we didn't involve the cell type information here, but kind of involved, because when we, for example, if we wanted to investigate the T cells, we will first inference the model in the T cell data, and then do this backpropagation.
Oh, okay.
So yeah, it's kind of use the cell type information.
Okay, thanks.
Okay, so so far this is basically like the provement of the gradient-based approach to see if that is effective. So next, what we really wanted to do is find the regulation relationship between different modalities. So we now added two kinds of attention maps together, and we can get these dual attention maps. And as you can see in this attention map, each point represents the attention score of a specific RNA elements and a specific ATAC elements. And we can pick these points with the highest attention score as the key points. And these points show that which RNA element focuses most for which ATAC element, and which ATAC elements are focused more by the RNA element. And since we have RNA elements and also an ATAC element for each point, we can link these two latent elements together. And then we can obtain these heterogeneously networks. And if we further use the gradient methods to find the genes and the peaks that corresponding to these latent elements, we can obtain this full graph. And in this graph, we can consider that the linkage between this peak and these genes, those peaks has the potential regulatory relationships. So to verify this, we first find those gene and peak pairs with this graph, and we use the high chip loop data as the ground truth to evaluate these founded pairs. And the results show that like there is a more than 60% of the found pair are overlapped in the high chip loop data. And so as you can see, this is actually an ongoing experiment. We only involve some very basic baseline, and we still need to involve some classical giant methods like Scenic Plus. And we also wanted to clarify that we do this. We didn't aim to extra better giant with our methods. We just wanted to know what's happening during the inference process and given some interpretation for the dual cross attention modules. So this is basically the current experience about scDiffusion-X. And so next step, we would like to further extend our model to larger scale and do some more challenging tasks. For example, for the single modality scDiffusion model, we wanted to extend that to larger scale pre-trained model and do the things like perturbation prediction and also like cell dynamic simulation task. And for the scDiffusion-X, we also like to involve more data and also possibly more modalities, and to make them a better models, because we wanted to know if the diffusion model could be a way toward the so-called virtual cells. And actually, I've been doing that for quite a while. I wouldn't go very deep into the version 2 of scDiffusion, but if anyone is interested, you are very welcome to discuss or even cooperate with me. Yeah. So this is it about my presentation today. So thank you very much for your attention. Do you have any questions? Yeah.
Before we open up the question section, let's take a moment to thank our speaker. Thank you, Arpai, for the wonderful presentation. And yeah, with that, we'll open up the questions, or the section for questions from the audience. Dylan, do you mind if I go first?
Please go ahead.
Yeah, all right. So just taking it back from your final slide, or second to last slide, it was a very natural, like maybe one before, the one with the multi-head attention, I believe it is. That's
This
basically a
one?
question. Yeah. When extending to more modalities over the dual channel attention you have now, do you think multi-head attention would be the thing you try now? Do you foresee any losses in switching out from 2 to more modalities, let's say, or anything that you have to sort of take into account as far as the design decision goes, so your model can be properly extended to multiple modalities?
So from the model size, I think the model is totally capable with more modality. I think the problem here lies in the data, since as I say, the scDiffusion-X is trained on the paired multi-omics data. So if I wanted to involve more modality, should different modality be paired, or can I find some way to like link these unpaired data with some kinds of method? I think this is the most critical problem. But for cross attention and these kinds of mechanism, I'm still very confident about its ability. Yeah.
Great, very good, concise answer. Thank you. Dylan, go ahead.
Yeah, so one of your slides are showing like the encoding and decoding processes, like the noising and denoising. And I think
yeah,
yes,
this
the
slide.
one you were showing just before this one, so it's probably the slide after this one, or okay, the other one, yeah, this one here.
This
Oh, that's
one,
diffusion V1. Okay, right.
Yeah.
Because I noticed that here you use similarity, SC similarity for the encoding part, but
Yeah.
I was like, I know that your group also have SC Foundation or Extremo-Gene-X, right?
Yeah.
So I'm wondering, was this work before working on Extremo-Gene and SC Foundation? Because you could have, I guess, put it in here, or is there something I'm missing?
So you want to know why is SC similarity here, but why not put SC foundation here, right?
Yeah,
Okay, the first thing is that SC foundation is not a generative model. So indeed the inputs of SC foundation and scDiffusion are the same, which both are expression profile of single cell RNA-seq. But the output of SC foundation is the representation of genes or cells. It's not designed to decode it back into the original space. And here we select SC similarity is because it's in a encoder-decoder structure.
Okay.
Its decoder can decode the latent representation back to the original space. But
I see.
yeah, but that's a very good question, because I switched that autoencoder in my next version of scDiffusion. As you can see that I changed it into a DQ autoencoder to, I think it can better tokenize the cell, since actually SC similarity is not pre-trained for generation, right? So I replaced this autoencoder to a module that has better scalabilities.
Yeah, because I mean, I guess in principle you could have had Extremo-Gene encoder and then just another decoder, whatever that could have been, right? I think.
Yeah, that could work.
And by the way, I was at ISMB and your group gave a workshop on it. So we met then. And I remember part of the workshop was explaining how you could do like perturbation modeling and you use gears as an example. So
okay, that tutorial, right?
Yeah, the tutorial. So I'm thinking like if you were to use SC Foundation as your encoder, and then you could even study gene perturbation in the latent space, right? Kind of recycle the setup you were showing in the tutorial, but kind of use it here somehow. I don't know if that makes sense. And then maybe just find a way to use another decoder.
Yeah, that totally makes sense. So you mean that I train another decoder incorporate with SC Foundation, right?
Yeah, something that would pair up well with SC Foundation. Because I think I remember reading the Extremo Gene paper, and there's a decoder, right? An Extremo Gene, if I remember correctly.
Yeah, they fine tune an actual decoder for a specific task.
Right.
Yeah,
Okay.
but they didn't pre-train that decoder. Yeah.
Okay. Yeah. Yeah. So okay. Although yeah, the VQ types of the autoencoders are also very cool and interpretable. So, but anyways, that was my question. So I don't want to capitalize.
But now that we're on that topic, like how about, I don't know, switching it to any other generative backbone? I don't know, trying a flow model in that space, or trying
Yeah, then that will be the flow, the cell flow by Fabien's group. Yeah,
I see.
they just published in that in I don't know, Nature Methods or something, or they just released that. Yeah, but yeah, cell flow is the flow matching model is we now consider that it will be more appropriate for tasks like perturbations, because flow matching is to switch data distribution from state A to state B, and we think that could be a very cool way to do tasks like perturbation. Yeah.
I see. So just like at a high level, very high level, just to say a few words on the matter, what should somebody be looking out for regarding the choice of generative backbone when they were to switch it in your model? Like, what are the maybe not precise trade-offs between different types of generative models, but more so in how does this choice impact whatever happens at the end of the model?
So you mean how to choose the generative model?
Yeah, that's right. Yeah.
How to choose that? I think that depends on the task you wanted to do. And also that depends on your computational resource and also your time requirement. Because honestly, diffusion model needs more time to training and to inference than the previous generative model like generative adversary networks or just the VAE. But however, the advantage of diffusion-based model it have better stability. It's easier to train, and it can give you a more stable and accurate result. So this is what you're going to consider when you're doing generation task. And if you wanted to do like more prediction task, for example, like perturbation prediction or drug perturbation prediction, then you have to compare the generative model with this regression model, like this transformer-based model. But I'm not very expert at this kind of field, so I'm afraid I cannot give you too many comments about that. But currently, I think for all kinds of tasks, which one has better accuracy, then you use that one. That's fine.
I see. That's a very comprehensive answer, I think. Thank you for that.
Yeah, thank you.
With that, do we have any more questions? We still got some time. Yeah, we got a raised hand there. Senior, please.
Thanks for your introduction and also the sharing. So actually, I want to ask something related to the project, like the ongoing project, like because I used to try to use the VQVE to do tokenization for single cell. It's also cell batching data, but I think I met some obstacles because I tried to do some. So the focus is kind of different than here. It's like we want to do tokenization, and then we want to show this tokenization somehow makes sense, and then apply that tokenization to representation learning models like Gene-Former Foundation, SC Foundation, and Astra. It's not for generation, but for representation learning. So basically, I think that the VQVEI trend, somehow if I try to analyze the latents, like the VQ latents, somehow it doesn't make sense at all. Like there is no biological signals, or it's very hard to find. So have you ever tried similar stuff? Or is it because like I train it in a wrong way, or it's not appropriate enough?
Actually, our groups is doing totally the same thing as you do now.
Yeah.
We wanted to use the VQ autoencoder to have a shorter tokenize for the input cell, because since you can now use, for example, like 32 tokens to represent a cell instead of use 20,000 genes, right? But it's very hard to explain or doing some interpretation for the code book, right? You want to explain the code book, right? And actually, it's very hard to explain all kinds of single cell foundation model, because this is also our groups are trying to do. We're trying to explain the latent representation of something like things like scGPT and SC Foundation, but we try many ways, but it's very hard to find reasonable biological meaningful things in these latent representation. And I am actually right now not very sure if these kinds of tokenization is the right way to encode the cell or gene data. But you mentioned that you're afraid that you treat the VQ VAE wrong, right?
Yeah.
I think the only matrix you need to concern about is the reconstruction performance. If the VQVAE can reconstruct the input data very well, then you probably treat that right.
Okay. Okay. Maybe we can discuss this later. There are a lot of details. Yeah.
All right. Do we have any more questions from the audience? Go ahead and then Chad, speak up. If not, I do have another one. Gene regulatory network inference is a huge field, and I saw that you had the scene plus results pending. And that basically just prompts a really quick question, right? Like, how does your Jacobian-based approach provide an edge over any of the traditional gene regulatory network approaches?
Yeah, we're still trying to make this comparison, because honestly, this experience is requested by our paper's reviewer, because at the very first beginning, as we noted here, we didn't want to extract a better gene regulatory networks. We're just trying to do explanations about our inference process. So we didn't really want to beat these classical John methods like Scenic Plus.
Yeah, because I believe it's Scenic. I'm not too sure about Scenic Plus, but they combine co-expression matrices with like motif enrichment. It's very biologically like rooted, right? It incorporates a lot of biological.
Yeah, they have a lot of like knowledge and many biological informations combined into their methods. So I guess I haven't get the result, but I guess it's very hard to beat them.
Yeah, that would be my hunch. But if you're in a comparable ballpark, I would say that that would very much indicate that your network is actually learning all of this biologically
Yeah,
relevant information. Right?
yeah. We just wanted to prove that there is biological meaningful things inherent in our cross-attention modules. Yeah.
I see. I guess I thank the reviewer for pointing out that comparison, but I very much would like to see this result as well in the future.
Yeah.
Dylan?
I hope this will going well.
Yeah. Dylan?
So yeah, about the so one thing that your model does that scenic plus can't really is the generative aspect, of course. So I wonder if one type of experiment that could be interesting is kind of, instead of doing like in silico gene knockouts, is doing like in silico regulatory element knockout, right? Where for maybe like for a given cell type, you look at some key regulatory elements that are deemed open in the data, and then you artificially shut them, right?
So
You shut them down. So is that something you?
So you mean to see this graph have any changes after we perturb the input data?
Yeah, well, so what this graph says in a way, I guess, is that you have regulatory elements controlling the expression of their target genes, right? But then the idea there is that for that regulatory element to exert a regulatory effect, it has to be accessible, right? That's, I guess, the whole biological mechanism. Well, the oversimplification.
That's a very great idea. We should give it a try. Yeah.
So you could, like, in this graph, let's say, in this graph, like number 61 regulates number 100, let's say. I don't know if I'm reading this graph right, but you could try shutting down number 61 and essentially make that regulatory element inaccessible. But then you could simulate what happens to transcription at the output, right? Some sort of conditional generation task. Where you corrupt the input, but in a very very principled way, because you generated the graphs that predicts what are the potential interactions, right?
Yeah. I think that's very reasonable. I probably will give it a shot about that. Thank you so much for this comment. Yeah.
And it really, it would highlight really like a key difference with your work, right? That's something that's
to these classical methods, right?
All right, so with that, if we don't have any more questions, thank you very much once more. That finalizes the 28th edition of the Multi-Omics Reading Group. Thank you everybody for coming.